start doing lesson 2.10, which is about tangent line approximation. And we're going to talk a little bit about elasticity of demand. And this is our last lesson for the chapter 2 before the big test. So first we'll start with tangent line approximation. And this is just another way of approximating a line which is tangent to a function, and just using that tangent line to actually approximate the function. So let me just show you real quick how to do this. It's not that hard, but it just involves derivatives. It's just another thing we can do. So the approximate function values using tangent lines, you're given a function and you need to find the equation of a tangent line. So once again, how do we ever find equations? We need a slope and a point. Well, they gave me half a point here, so I need to find my y by plugging this into the original. So that would just be the cube root of 45 minus 18, or the cube root of 27, which is just 3. So that's my point, 1, 3. That was pretty easy. You just plug in 1 into the original and get your point. But to find slope, you need to take a derivative. And so again, derivative is, slope is the derivative, excuse me. So this is a u problem. So this is like u to the 1/3. And so the derivative of that would be 1/3 u to the negative 2/3 times the chain. And if we substitute u being what's underneath our square root, we would have 1/3 times 45x to the 3rd minus 18 to the negative 2/3 times the derivative of this, which 3 times 45 is 135, x to the power of 2. Okay, and we just need to plug a 1 in everywhere c and x, and that'll tell us our slope. So 1/3 times 45 minus 18, again, that was 27 to the negative 2/3. And then 135 times 1 squared is just still 135. And you can just simply put that in your calculator. 1/3 times 27 to the negative 2/3. And times 135. And you get 5. So our slope is 5. So to write an equation of a line, remember, it's y minus y1 equals m times x minus x1. So y minus 3 equals m, which is 5, times x minus x1, which is 1. So that becomes y minus 3 equals 5x minus 5, and then add your 3 over. So your L of x equation, your tangent line approximation, your tangent line equation would be 5x and then minus 2. And now on part B, they say, okay, we'll use that tangent line to approximate the f of 1.1. So we're going to take 1.1 and we're going to plug it into this equation right up here. So we're going to do 5 times 1.1 minus 2, so 3.5. But now on part C, it says, okay, we'll compute the actual value of 1.1 in that function. So we're going to plug 1.1 into f, into this function up here. So using my calculator, I would have 45 times 1.1 to the 3rd, and then minus 18, and that's all to the 1/3. And I get a very large decimal, but it's asking me to calculate the error. So the error is just the difference between 3.5 and this 3.47. So I'm just going to subtract the 2. 3.5 minus the 3.47, hit enter. and I get 0.0268. I believe they want you to do like 5 decimals, 0.02687. I think you could go further, but that's it. So it's not too hard. It's just using this idea of derivatives and being able to now get a kind of close approximation to what like a decimal would be. Like if I were to say, okay, well, what would 2.79 be? And you could, use this tangent line to get yourself a guess, a near value. But thankfully with the calculators make it much easier for us. All right, so you'll have a few questions on tangent lines. Now let's do something called elasticity. So if you are working for a company, retailers and manufacturers will often, they need to know like what a small change in the price how it would affect the demand for their product. Like a small, tiny change. Like if I change the price a little bit, would my revenue go up? Would it go down? Would it stay the same? And so there's this idea called elasticity in business and economics. And what it does is it measures the sensitivity, there we go, of demand to an increase in the price. The sensitivity of demand to an increase in price. And so the formula for elasticity of demand is the function E of x being defined to be negative x times d prime of x over d of x. And if you remember from what we've done in the past, d of x is your demand price function. Now, just a couple of things to talk about. When this elasticity function has a value that is less than 1, what that means is that the total revenue is increasing, while meaning that the demand is inelastic, is what they say, inelastic. In other words, an increase in price will increase your revenue ever so slightly. Okay? So your total revenue is increasing. Your demand is what they call inelastic when it's less than 1. So 0.5. Not bad. Things are going up. We're good. However, if I have an elasticity that's greater than 1, then my total revenue is actually decreasing. And my demand is what's called elastic. And what that means is an increase in your price, because remember, that's what elasticity is about, increasing the price. Your revenue is actually decreasing when your elasticity is greater than 1. When it equals 1, that's when your total revenue is maximized. It's at the highest it would go for that particular product. And we call the demand unit elastic when it equals 1. You're definitely going to want to put this, memorize this, put this in your notes. So less than 1 is inelastic, greater than 1 is elastic, equals 1 is unit elastic, which is maximized. And then obviously this formula. So let's actually apply this to some problems now. So this would make a little bit more sense. So a company found the demand for its product to be d of x equals 400 minus x. Find the elasticity function, find the elasticity at a price of $124, and then determine if it's elastic or inelastic, and then find the price when the revenue is maximized. Okay, so that formula again is E of x equals negative x times d prime of x over d of x. So we're going to take this formula, d of x, we're going to take the derivative of it. Just super easy, -1. And we're going to rewrite this equation. So this would be E of x equaling -x times -1 over the original function. Or a better way to say would just be x over 400 minus x. There's your elasticity function. Now we're going to find the elasticity at a price point of 124. Let's see what's that doing if I increase the price to 124. Is it going to increase my revenue? Is it going to decrease my revenue? And that's depending on what I get out here. So let's see. E of 124 would be 124 over 400 minus 124. So 124 divided by 400 minus 124. 0.449. What does that mean? Well, that is less than 1. And again, if you are less than 1, you're inelastic, meaning you can increase the price a little bit and you will get an increase in revenue. The total revenue is increasing. It's inelastic. Okay? An increase in price will increase the revenue. Well, let's find the price that we could go up to and get our max. You know, that would be really good. If 124 works, let's find out that max. So what do? We actually take the elasticity function that we found and we just set it equal to 1. Because that's where it's maxed, when it equals 1. So x over 400 minus x equals 1. And I just like to do this. So that would be x times 1 is x equals 400 minus x. So 2x equals 400. So x equals 200. At $200, I would probably have a max, a unit elastic. All right, let's do one more. Same idea, just a little bit harder of a derivative, honestly. Okay. So a company found demand for its product to be d of x equals square root of 600 minus x. So there's that chain rule coming by. So elasticity again, the function says it's -x times the derivative over the original. So let's find our derivative here. This would be, again, this is 600 minus x to the 1/2. So that would be 1/2 times 600 minus x to the, take away 1, -1/2, times the chain of that, which is -1. So -1/2 times 600 minus x to the -1/2. That's our chain. That's our derivative. All right, so now I'm going to put this into this equation. So, oops, right? E of x equals -x times my derivative, which is -1/2 times 600 minus x to the -1/2. Oops, sorry for squishiness. Over the original. And I'm going to rewrite the original like this. Now let's see if we can clean this up. So -x times -1/2 would be positive x. Well, positive 1/2 x. This 600 minus x to the -1/2. Remember, that can go to the bottom. And then I can, since these are the same, if I bring this down, this would become 600 minus x to the 1/2 and another 600 minus x to the 1/2, which means there's one whole of those quantities. 600 minus x, there's one of them. So this comes down, and you would have 600 minus x to the 1/2 times another 600 minus x to the 1/2. Now, one more thing we could do about this 1/2, I don't like it there, so I'm just multiplying the top and bottom by 2, so I'm going to put it on the bottom. 2 times 600 minus x. So that is your elasticity function. There's your part A. Now let's use that to do part B, which is to find the elasticity at a price point of 500. So I'll move my part B here, kind of moving around. So this would be E of 500 equals, I'm just going to put 500 into my elasticity function. 600 minus 500. And that's 100 times 2, so that's 500 divided by 200, or 5 halves. Now, is that greater than 1 or less than 1? Well, that's definitely greater than 1. And again, if you're greater than 1, going back to this, greater than 1 says that your total revenue then is decreasing. That's not good. Your demand is elastic, okay? So it is elastic. So let's find the price for which it was revenue. The revenue would have been maxed. 500 is a little too big, so let's find the price. So again, take your elasticity function and set it equal to 1. X over 2 times 600 minus X equals 1. And I do a little crisscross. So that would be, let's scroll this up. 1200 minus 2x equals x. 1200 equals 3x. X equals 400. We should have maxed it at 400. Our price would have a revenue max at 400. Hopefully this is helpful. It should be easy homework. You just have to do the quiz 2.10.